Okay, thanks for coming back. So in this last hour, we are going to present the solution, take some questions from you guys. I hope you have some. And then Max will continue with another demo and some advanced features of Flink, like some internals. Yeah, so the task that you had was this mail count task. It was very much related to the word count task. And yeah, let's have a look at the data set you had to use for this. So it was this file here, which is just a sec, which is the archive of the Apache Flink mailing list actually, and you see you see a message ID, a timestamp, and the author. So the task was to analyze this data and do some basic counting. So not the most fanciest application of Flink, but this should really get you started with the API and should make it easy for you to also branch off to more advanced applications. Max will cover later. Yeah, so if everything worked out, you should have seen something like this. And it had some to-dos in it. The first one was to adjust this path to the file. So yeah, we're going to read the file we downloaded. And the entry point to all Flink programs, or to this in particular, is the main method with the execution environment for the client. And yeah, maybe just let's start by just reading the mails and printing them out. So the real data source Max talked about earlier, this was also taken care of by the CSV file reader, where we said, okay, this is the path, fields are delimited by the symbol, and we are interested in the second and the third field. So the actual data format we saw on the terminal was like 5 fields, but we only need 2, the timestamp at the sender. So this was taken care of. If you now print this, this is just a data set, nothing fancy. Any questions up to this point you had maybe regarding the execution environment or something? Okay, no, that's great. So the first task then was to extract the month and the email from, by the way, is this too small or is it good? Okay. Was to extract the month and the email from the 2 fields. So you had to implement a map function to map each row to this new extracted row. So this was the mail month email extractor function you had to implement. So the input looks like this, which is basically a string timestamp and a sender in this format. So what we needed to do was to get rid of essentially this suffix here, because we wanted to group by the months for each sender. And yeah, you had some helper methods for this one as well. And yeah, you had to return a new 2-tuple with the same type. So this was a string, this was a string and stays a string. And you had some helper methods for this one as well to extract the email address. The first one is the timestamp. So you take the first field and extract the months and put it back into the tuple. And you do the same for the email address. Maybe let's do it like this. That was the first part. Any questions? Okay. So now, if you execute this again, you will of course, see it in the desired format. So it's just like the month and year and the email address. So what you also will see is that there's actually a lot of noise. There's a lot of like emails from git@git.apache.org and Jira. So we wanted to get rid of this as well. That was the next task, to apply a filter transformation. And the filter, yeah, it just gets an input and then returns either true if you want to keep the input, or false if you don't want to keep it. Yeah, so in this case, we are filtering by email address. So we could have said something like return, so return the negation of if the email address, which was the second field, does not equal this one or the other one. I'll just keep it like this for now. Is this correct? So if it equals, if the email field equals this email address, we skip it. Otherwise, we keep it. This should reduce the noise, and then we can continue. So the next step was to now we have like transformed all the fields and brought them into a format we want. But now we want to group them and count them up. So what you can do now is this group by operation. And what's actually quite cool about Flink in this case is what also Volker talked about, that the data model is not just a key value. So you can specify here arbitrary fields to group on. And the exercise actually said that you have to group on both the months and the user email address. So in this case, you can specify both indexes to do the grouping. So you group by both the timestamp and the sender. Oops. And after the grouping, you can apply a reduce transformation where you get all the group values here. So and collect some new values with the output collector. So what you had to do in this case was to return a tuple 3 though. So because you want to add the count. You get tuple 2s with the name and the email address, and you add the counts, right? So at the end, we need something like this to collect the 3 tuple. And before, we have to iterate over all the elements. So we do this like this in a for each loop. We need the count. Start with a 0, and for each element, we increase the count. And what's missing is that we need to also know for which sender and months we are counting. So we just store it here, maybe like this. There are also other ways to solve this. So this was the first field, the sender was the second field. And now we should be almost all set. We wanted the 3 tuple with the months first, the sender second, and the final count. And this gets collected. And now, if I didn't mess anything up, this should be fine. So we can run it.
Let's see. Seems to work.
Yeah, it seems to work. So, for example, Max in the 3rd month of October of this year wrote 30 emails on the mailing list, and other guys as well. Yeah, this is maybe not that interesting right now, but should have given you a feel of how the stuff works. Does anyone have any questions? Okay.
Did you all manage to complete the exercise? Okay, some of you.
Yeah, so, and if you want, you can also do, there's also another exercise, you can read it up here. It's similar, but you need to use a more advanced operation, like a join operation. And there's also another Flink training website, which is also linked in the slides, where you have even more exercises. For example, with the Jelly API, which is Flink's graph processing API, Max will also talk about it, and yeah, some other stuff. Okay, then I think Max will continue with some further slides if you don't have any questions. And also feel free to provide feedback if you think like you would do some stuff differently for the training.
Definitely.
That's always valuable for us. Yeah. Okay.
Whoa. Okay. I hope we don't bore you too much with all this information, because yeah, we know there's a lot to learn about Apache Flink and can seem overwhelming. So if you have any questions, just ask. We can talk about that one longer and can skip some of the advanced stuff maybe. So it should be, I mean, the goal is that you get familiar with Apache Flink and not be like confused. Okay, so if I manage to cover everything in the advanced part, which kind of doubt now a bit, it's a bit late already, I want to talk about the special batch features of Apache Flink that yeah, we built for batch processing specifically. And I want to talk about iterative processing, which helps you to construct loops in Flink, which can be used for example, graph and machine learning library. Then I want to talk about fault tolerance, also give a small demo, and then talk about show you some more transformations and some advanced API concepts. So what is special about Flink that not only applies for the batch part, but is used there especially, is that Flink uses its own memory management. So typically in a Java program, you would, if you create objects, you would allocate them on the heap. And once you run out of memory, you get for example, out of memory exception. So we figured that we need some kind of more sophisticated memory management in Flink. That's why by default we divide the Java memory, the Java heap also, we also call it Java heap, into 3 parts. So of course we need some basic memory for Flink for its runtime. And then we allocate quite a huge amount of the free memory for the managed memory. And that's actually where we perform all the specialized operations in Flink, if we can, like sorting, or special implementation for hashing that works on these managed memory pages. And also the serialization always goes through this memory. And then we have the remaining heap, which is used for your own functions, so where you can allocate objects. So that's actually a really cool feature, because it means that when Flink deals with data, we cannot basically die because of out of memory exception, because what we do is when we receive the data, when we send out data, we serialize it and put it into the managed memory. So, and this managed memory is partitioned into memory segments. And we always know like how many memory segments we have left. And if we don't have any left, then we can start writing to disk, which you can see here. And we always try to run everything in memory, but if we run out, we put it to disk. And then later we can also work on the memory and later restore data from disk. And that gives a very robust behavior for a lot of applications. Of course, you can still run out of memory if you, here in your user function, start to allocate memory like crazy, but yeah, that's more difficult to do. Yeah, and we did a little bit of benchmarking to test the managed memory behavior. So what we did is execute a hash join. Well, you don't need to know what a hash join is, but if you know, it's nice. So there's two inputs for the hash join: a probe and a build side. The probe side was fixed, and the build side is variable. And we can see here that when we increase the amount of data for the build side, at some point, this was on Google Compute Engine here, we ran out of managed memory. And so, of course, the performance degrades, but we can still run the join and don't run out of memory. Then another interesting aspect already mentioned is the optimizer. It also works especially well for batch programs. So the basic idea is, like Volker already mentioned as well, that we figure out based on the program and based on sampling some of the data that the program uses, what would be the best way to execute a data flow. So here, for example, we perform a hybrid hash join, and these are basically two strategies how this could be executed. So in one case, we just hash partition and shuffle the data. In another case, we broadcast one side, the build side, to the join operator, which can be more efficient if you have a small data set on the broadcast side here. Yeah, but we don't need to worry about it, but it's a really cool feature, and yeah, it will also be extended further, I guess. And yeah, for having some kind of SQL-like functionality, because a lot of people ask for it, in Apache Flink there exists the table API, which was developed recently by a student, and which is a really cool way of just selecting and joining data if you don't want to do very sophisticated data analytics. So here, for example, you can create two data sets by just reading from a CSS file and filtering elements. For example, here a marketing segment, and you can also, like in SQL, assign special names to columns, and then it's pretty much a mixture of the data set or API and some SQL syntax. So you join here, and you can always specify the join conditions using SQL-like syntax. Yeah, so I think it's a pretty cool feature. Any questions? Okay. Then I mentioned that we have the Hadoop MapReduce compatibility, also for the batch part, which means you can reuse MapReduce functions and input and output formats, and also types. Hadoop types is also supported very well. So now we come to the iterative processing. To understand that, I want to show you a way to. Volker also showed the slide, by the way, but I want to show you again, like what would be like maybe a not so native way to execute iterations. You could just simply say, okay, I have a job, and like also cascading or other frameworks on top of MapReduce do it, Hadoop MapReduce do it. Like we would just generate a bunch of jobs and chain them together and kind of simulate that way an iteration. But in Flink, there's native support for iterations, which means that in principle we allow cycles in the graph, in the execution graph, which gives us a way to feed data back into an operator and feed it in there multiple times. And we have this concept Volker also mentioned of delta iteration as well, which means that over time, the algorithm might perform less and less updates on the data, and that way we don't have to push all the data in again and yeah, process the remaining data faster. Yeah, where can you use this? We have basically two use cases. Of course, you can use it for your own programs, but libraries like Flink ML or Jelly also heavily rely on it. And if you're into machine learning, this is a very like similar machine learning or inspired machine learning library like scikit-learn in Python. And you have I mean, it's still growing, but you already have a bunch of algorithms like support vector machines, linear regression, optimization algorithms, ALS. Yeah, and it's a really nice API. It's very similar to scikit-learn. Yeah, then there's Jelly. If you have any questions, you can also ask Vasya here. She's the main contributor to the Jelly API. Yeah, you have a bunch of graph algorithms and different ways of writing graph programs, like from a vertex point of view or from the edges. Yeah, if you're into graph processing, this is a great library, I think. And yes, and to see if that really scales well, the iterations, we did an experiment using the ALS algorithm that is also implemented in the machine learning library. So we started a Google Compute Engine cluster, and it does not mention here how many machines it were, but I think it was 40 machines, and ran a matrix decomposition algorithm to compute recommendations. So basically, you have this rating matrix, and it's sparse. It has ratings of users, and you want to decompose it to generate recommendations. And we found that in this experiment, we had a really nice scaling. So with different number of items in the rating matrix, we achieved really nice scaling. And if we increased the number, the machine type even further, like gave it more memory, then it performed even faster. So yeah, there's also a blog post about this. You can read it on the Data Artisan's website. It has all the numbers. It's actually a very big blog post. Yeah, and it's separated into 3 parts. It's if you're really interested in it, you should check it out. So now I want to talk about fault tolerance, especially fault tolerance in streaming. I know that Paris and Gyula will talk about it also on Saturday, but we have a nice demo which I think you will enjoy. So why should we be fault tolerant? I mean, why should we care at all? Because I mean, I'm presenting now, and I mean, my laptop it actually crashed while I was away. That's not a good example, but yeah, I mean, of course, failures occur not very often, but the more hardware you have, the more complex your programs are, the more likely they are. So, what can we do to cope with faults? In the batch part, it's a little bit easier because there we can just use the simple strategy and restart the job or task depending on whether what component failed. And we can either just reread from the entire input again, and okay, it will take a little longer, but we can just restart the job, or also from intermediate results. But in the streaming case, it's a bit more difficult because we might read from a continuous input source where we cannot easily say start from there again. And we might lose some of the data, and especially the state of the operator. So if we, for example, train a model using an input stream and store this model in the state of the operators, then you basically lose it, and you need to persist it somehow. And you also need to ensure you start at the correct offset, and that is at the sources, but also at the individual operators, because you don't know when data enters the streaming program, where like at which stage it is inside the data flow. So there are basically two types of guarantees for streaming. One is called at least once, and the other one is called exactly once. Yeah, and at least once is a weaker guarantee because it just says a tuple will just, or data will just flow at least once through a data flow, but it could also flow through it several times. What exactly one says, it really goes only through the program once. And yeah, this is the first one is easier because you could just start for example, use Kafka and start at the same offset, or persist the offset, for example, and start there again. But then you don't know about the internal state. So to achieve exactly once, you need to also back up the state of the operators. And yeah, don't want to go into too much detail because I know Yula and Paris want to say something about this, but there are different approaches to solve this problem. In Spark, they do like mini jobs, like we heard before, and that works well, but it chooses quite high latency, and yeah, it can be tricky. I think if the state gets bigger. Then there's Google Millwheel, which they have a really fancy key value store that supports transaction, where they persist the state for every update they perform, every record basically. And then there's the Flink approach, which uses a distributed snapshotting algorithm called Shandy-Lamport. It's not really state of the art, but it's a, I mean, it's from the 70s, I think, but it's a really nice algorithm. And I want to show you a little bit how it works, because it's not so complicated, the basic principle. So if we have a data flow program here, and these are the sources, and these are sinks, and here at the right, then to create a checkpoint while the Flink job is running, the job manager tells the sources to emit barriers, which these are these yellow rectangles, and these barriers go, because it's directed flow here, go through the graph towards the sinks, and every time they reach an operator, they ask the operator to create a snapshot. So the operator will, I mean, it's not I won't cover this in detail, but the operator will find some way to persist its snapshot. And once, yeah, this will happen several times from all sources. And once all markers here barriers have reached the sink, then we report that to the job manager. The job manager knows that a consistent snapshot has been made. Okay, so we believe that this gives, it gives quite low latency because it can be performed asynchronous, and it gives exactly once guarantees because it's based on the Shandy-Lamport algorithm, which guarantees that. And we found that it, of course, had some impact on latency and throughput, but it is, because it's adjustable, it gives rather nice performance, although, of course, there's an overhead for fault tolerance. Yeah, and now I want to give a demo to demonstrate that it actually works in Flink. So, do you want to say something about it? Okay.
So essentially, it's the same program we had in the first demo for this Wikipedia edit stream. And what Max is going to do is to just randomly shoot down task managers and then show that this is recoverable.
Yeah. So we will modify our program a bit to actually introduce an operator which contains some state. So here we just wrote our the count of the edits within the last 5 seconds we converted to a string and wrote it to a Kafka source again here. So we will do something different here. We will create a counter, which doesn't do really much. I mean, it's a map function which has an internal state. This is the count. And every time it receives a tuple, which is the channel, the username, and the number of edits the user performed, it takes the number of edits the user performed, adds it to the count, and emits a string which says count and gives it the actual count. And we have these, because it's stateful, we have this checkpointed interface which has 2 methods to get the snapshot, which just returns the count, and restores it after a failure with the restore state method. Okay, and I need to change one more thing to ensure proper fault tolerance. I need to change this a bit. I need to use the persistent Kafka source and configure the snapshotting interval. 500 milliseconds should be fine. Yes, and now I will bring up the Flink cluster, and I can verify it's really brought up by maybe opening my browser. I don't know. So there we go. This is the web interface. So we have one task manager, one processing slot. And now I'll bring up my Zookeeper and Kafka and some exception.
Are not found?
Yeah, wait.
Okay, now it's running.
Oh. Okay. Okay, why does it not work?
The config path. That's what he didn't find.
This one?
Yeah.
Ah, it's not complete. Okay. 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 Yeah, that was an issue with the path. Yeah, it wasn't complete. So now we have the Wikipedia source up again. So we can check that by reading again the raw input from Kafka. So thank God it works. So we have Kafka up and running. What I now need to do is, because I'm running it with a Flink cluster, submitting it not with the IDE, I built Another oh, I'm not in the right direction. I built the project we created using Maven. Now that is done. So now I can submit the program to a Flink cluster. So now I submitted the program we just created with the stateful Kafka persisting Kafka source and the stateful counter to the Flink cluster. And again, we will just read from the Kafka source to verify that this actually worked. Okay, so it looks like we are emitting these count messages now every 5 seconds. And of course, if the streaming fault torrents work, we should never see a decrease in this counter. It should never start from 0. It should always be increasing where it left off, if in case of a failure. So of course, it doesn't make sense to test fault torrents if we don't have any backup workers or task managers. So we have just one. If we kill that one, we cannot do anything anymore. So I will start another task manager, and we will see here in the job interface, in the web interface, that we now have 2 task managers. One is running a stream job, the other one is doing nothing. So what I will do now is to kill one of the task managers. So you can see them here running as processes. Will probably be the one with the lower pit. If not, then we can retry it. So now I'm killing it, and we should see that the job failed. So it failed here. We got an exception, but it switched to the state failing and afterwards to restarting. So now the job, as you can see, was restarted again. And we see the count is increasing again. Every 5 seconds, of course. Yeah. Any questions?
Where is the state stored?
The state is stored in Zookeeper. I mean, the state handle is stored in Zookeeper, which is also started on my machine.
I thought Zookeeper was stored just by Kafka.
No, Kafka. Kafka and Zookeeper are independent. I mean, Kafka runs on top of Zookeeper. Yes.
What is the overhead for, so how much logs are generated for and stored in Zookeeper, or how is the flushing, or what is the average like flushing period for Zookeeper, because Zookeeper will saturate at some point.
Yes. The actual state is not stored in Zookeeper, but only a handle, like a file path, is stored there. And the state is, which just points to the state. And the state can be stored in, usually I think it's an HDFS. No?
So at the
Yeah.
moment, maybe Paris.
Yeah.
In this example, we're using memory replication. So we just replicate the state in the DOM manager.
Mm-hmm.
But you can also choose HDFS.
Did you get this?
Yeah.
So in this example, it was just a job manager for the state backup, but we have different backends. Like some persistent storage could be HDFS or anything else.
And
Yeah.
and also like now when you kill that, so there are different set of operators, right? So
Yeah.
when you kill the task manager, so which operator checkpointing regularly, right?
Yeah.
So in case of failure, how do you monitor the consistency among
So
the
you go back to the last completed checkpoint and restart the complete job from there.
no consistency between set of operators? Like, so if you have a three-stage DAG,
Mhm.
and then the second stage start to fail, but the downstream operator they don't know about. So how you have maintained
Yeah.
consistency between different
Yeah.
stages?
I mean, all operators back up their state individually, and if an operator fails, then the job has to be restarted. The job manager will detect the failure.
All of them.
and-
Yeah.
All of them, of course. Yeah.
There's another question.
What happens if a job fails over and over again?
There's a configuration that you can set how many times it should retry. But if it fails and fails, then we
For
cannot do
yeah.
anything.
If it's I don't know if the problem is in the user code, there's not much you can do about it. So in the sense of I don't know if you
It's the virtual machine problematic.
sorry.
Probably it's the virtual machine problematic, and this is why it fails again and again.
Yeah.
Could be, yeah.
Yeah, or I don't know, you programmed a user null pointer exception in your user code, and it always hits this, then it will always restart, and there's really actually nothing you can do about it.
I mean, the thing is,
But
if the
it-
task manager fails, if the VM is problematic, then the same task will be deployed in another VM when you recover, right? Upon recovery.
Yeah, but then it will not fail again, right? That
Yeah.
was-
The new VM might be okay, right?
yeah. Yeah.
If we try to compare this streaming API with the storms,
Mhm.
storm, so they make note of the ID of each record and they acknowledge it in every state of the DAG cycle, so that it only processes it if and only if it receives an acknowledgement,
Mhm.
then it will go forward. So that kind of mechanism is not available in Flink right now, right?
Yeah, but you don't need it, right?
So,
The-
so there, in Flink 0.10, there is at least one guarantee option that does more or less this, but with a barrier.
But you use Kafka as your main.
No, we don't use Kafka for backend at all.
All right. Okay, we have like 10 minutes left, yeah. Oops. Wrong slide. I'm thinking what would be a cool thing to do now. Maybe give you an introduction to some more transformations you can do in Flink.
So we have like 5-7 minutes.
We have 5-7 minutes. Okay.
Just come over maybe.
Hmm?
Just skim over it without the reading.
Okay. Okay, yeah, here I wanted to talk about the type system, but it's probably not so interesting. Yeah, I'm gonna skip this part. I mean, you can use also POJOs, your own objects as data types, and that makes it also possible, or you can also use this syntax to select fields by name then, which is nice because you don't have to remember like was it the first or second field. And yeah, Scala case classes are also supported. Yes, and it's also possible to select nested fields as keys for grouping, and also use select multiple fields from an object. So, and we already saw in the exercise that you can group on several keys. It's also a nice feature. Yeah, of course, Flink will always warn you if you, for example, join datasets where you specify not compatible join keys. For example, here you have a string and a long, and of course you cannot compare these easily. So we only talked about basically these operations, and also in the exercises we didn't cover more, but there are actually more in Flink. So we have this Hadoop kind of style reduce, where you just return one value. You have the co-group, and we have of course support for combiners and special support for grouping groups, which you and union operator, like you know from SQL. So yeah, maybe show you the co-group. It's nice because it's an operator you can use to group two inputs on a key and receive as an input the elements which are present in both inputs, and that enables you to implement all kinds of join algorithms. For example, here we have a co-group function which just emits elements where if the right-sided data set contains elements, and this is like implementing a normal SQL join, an equi-join manually with a co-group. So it's a very powerful concept if you want to have very flexible control over how you join data sets. Then of course we have combiners, and combiners you already know about. In Flink you have explicit control how your combiner should look like. So you can implement this rich group reduce function, which you can specify a combine function. Yeah, that's pretty much it. And you can specify the order, the sorting, which is performed internally in Flink when you group elements. You can directly specify the sorting, which then you don't have to do it in user code. One thing to watch out maybe is that you can also do an all group, an all reduce, which this is a special function, but it means that the parallelism is going to be 1. So all the data will go through one machine and be reduced there. That can be very expensive, but sometimes it's necessary. So just something to watch out. And of course, union operation is very simple. Just just unite two data sets, which give you all the elements of both data set. Right. Then we have this notion of rich functions, which are basically available for all kinds of transformations. And these have additional methods like open, close, and get runtime context to execute something before the actual user function is run, and after it has run, and to access some of the internal features of Flink, like get the index of the parallel instance. Like if we have 8 parallel instances, that you will get a number from 0 to 7, and it gives you access also to the execution config. And accumulators. Accumulators are like counters in Hadoop, if you have already learned about this. So I think I'm not going to go over the advanced API concepts now, which would be like broadcast variables, which allow you to broadcast a small data set to all instances of an operator. Yeah, because I think that would take too much time. Instead, I would like to encourage you to experiment with Apache Flink and give us feedback on the user, or if you're a developer, if you want to become developers on a developer list, mailing list. We are very active there. It takes under an hour usually for a response to come in. And we are always looking for new people, of course, who want to contribute. If you just want to follow what's going on with Flink, you can subscribe to the news mailing list and add our blog to your feed reader, or follow us on Apache Twitter. And Apache on Twitter. It's not an Apache project, not yet. One more thing, there's a conference on the 12th and 13th of October in Berlin. And Volker mentioned already there's a discount if you want to attend. And definitely if you have something to talk about regarding Flink, you should submit an abstract. It doesn't have to be a full paper. Yeah, and that's it. Thank you for listening.